What's up, everybody? Today we're talking about waves, which is described as the motion of a disturbance. Okay, that's going to be our working definition for waves. Here's some key terms. You guys can press pause, read through these, take notes if you need to. Medium, which is a physical environment that a wave travels through. Most waves go through a medium. These waves are called mechanical waves. If a wave does not need a medium to travel through, that means that it is not a mechanical wave. All right. It means it does not need particles to vibrate. Amplitude is the distance from the center of the wave to the top or the bottom, which we're going to get into. Wavelength is the length of a cycle, either crest to crest or trough to trough. By the way, if you don't remember what a crest is, it's the top of a wave, and the trough is the bottom of a wave. Pitch is how high or low a sound is perceived. So a high pitch goes hee, low pitch is low. And frequency is the number of times a cycle is repeated per second. So one cycle is all the way up like that. So if it does 2 of these in 1 second, that means that the frequency is 2 hertz, Hz. We're also going to go through longitudinal and transverse waves, constructive and destructive interference, and we're just going to take a short look at the Doppler effect. So first of all, we have amplitude. Amplitude is the distance from the center, which is the middle line there, to the top or the bottom of the wave. Take a couple seconds to try and guess what the amplitude of this wave is. The amplitude is 0.20 meters. All right. Next, the wavelength versus period. Wavelength and period, they kind of look the same because you find them the same way on a graph. The only difference is with the wavelength, the length of one cycle. It's the length of one cycle. Wavelength is a length. It can also be found as the distance from crest to crest or trough to trough, but you find this on a distance versus distance graph, like the top graph that we have on this page. The period is the time it takes for a wave to undergo one cycle. So it can also be found as the time it takes for the wave to go from crest to crest or trough to trough, and you find this on distance versus time graphs. So the only difference between finding wavelength and finding period is the type of graph that you're looking at. We're mostly going to be dealing with wavelength, and that is going to be a distance versus distance graph. How much it's going up and down versus how much it's going across. So amplitude and frequency and what it has to do with loudness and pitch. Now, I don't know if you've ever recorded yourself or seen somebody recording and you see the bars jumping up and down. Those bars actually represent the amplitude. And so when the bars are low, when it's a low amplitude, it's a quieter sound. When the bars jump up high, then that means it's a louder sound. Now, that has nothing to do with pitch. You can have a loud high-pitched sound, or you can have a loud low-pitched sound. You can have a quiet high-pitched sound or a quiet low-pitched sound. Amplitude only affects how loud it is. Now, what affects pitch is frequency. If you increase the frequency of the sound, you get a higher pitch. If you decrease the frequency of a sound, you get a lower pitch. Now we're going to take a look at transverse and longitudinal waves. A transverse wave, particle moves perpendicular to the direction of the wave, so the particles go up and down like this. And longitudinal wave, the particles move parallel to the direction of the wave, so the particles move like this. So as you can see, these two examples are done on a slinky. On one slinky, you see the coils moving up and down. Notice that the coils don't move across the screen. They just move up and down. The wave moves across the screen. Same thing with the longitudinal wave. The coils aren't moving across the screen. the compression is moving across the screen. And let's take a closer look. So with longitudinal waves, I want you guys to look at these particles. What you'll notice is you'll see the waves slowly moving across the screen. Now, if you concentrate on the particles, you'll notice that they're only moving back and forth. The one particle is not moving across the screen. So you can tell that with the red particles that have been highlighted. Now, in order to label this to make it easier to see, let's take a look at this. So as you can see, the particles are moving back and forth, but the wave is what's moving across the screen. And where you see the high concentration of particles is called a compression. And when the particles are spread out, that's called a rarefaction. Transverse waves are very similar, except as you can see, the particles are moving up and down instead of moving across. But the wave still is moving across the screen. Next, we're going to look at constructive versus destructive interference. Now, first of all, let's talk about what interference is. Interference is when two waves interact with each other. So there's two different types of interaction. It's either constructive or destructive. If it is a constructive interference, then when two waves interact with each other, both waves are either up or they're down, and you're going to add the amplitudes. When they're destructive, they're in opposite directions. So one is up and one is down. They hit each other. You subtract the amplitudes. We're going to take a look at an example where we're going to use two waves of the same amplitude, and you're going to see what happens when they interact constructively and destructively. Here we go. So as you can see, they're moving in the same direction. Once they hit, they double in size because one of them is 0.5 and the other one's 0.5. When they clash together, they give you 1. Now when they're opposite sides and they clash together, you'll see that they make a wave of amplitude 0 for a split second. Now if they're both negative, the same thing happens. You have negative 0.5 plus negative 0.5 giving you negative 0.1. Alright, so those are your three examples. By the way, what you're seeing here are pulse waves, and it's a wave that consists of a single traveling pulse. So what you're seeing in this graphic is two pulses interfering with each other. Now we also have the Doppler effect, and we're just going to quickly look at this. It's an increase or decrease in the frequency of a sound, light, or other waves as the source of an observer may move toward or away from each other. The effect causes sudden change in pitch, noticeable in a passing siren, horn, or car. Now I'm sure if you've cut somebody off in Houston traffic and they're beeping you as they're speeding past you, you hear a change in pitch in the horn. You hear wow. That change in pitch is because of the Doppler effect. Now, usually the sound will emit with even circles radiating out. But in this Doppler effect, the moving source, the car, when it's moving towards the person, you can see that the frequency is higher because the lines are closer together. So that means each wave happens quicker. So the person is going to experience a higher pitch than the sound actually is. Now, once the car passes, the observer is going to get the other side of it, which are the wider rings, which means the frequency is lower than the actual sound is, which means the car is going to sound lower pitched than it actually is. Lastly, we're going to look at wave speed. It's a simple equation. V equals V meaning velocity or speed of a wave is equal to lambda. That funny looking letter is a lambda. It stands for wavelength. You could think of it as L for length, units of meters, times frequency. Frequency is, as we said, the number of times a cycle occurs per second. So you can think of the units as being per second. So meters times per second gives you meters per second, so it makes sense. So to solve for lambda, you just need to divide both sides by f, which will give you v over f. And to solve for f, you're going to divide both sides by lambda, which will give you v over lambda. So here's a quick question. The red light emitted by an HENE laser has a wavelength, lambda, of 633 times 10 to the negative 9 in air, and travels 3 times 10 to the 8 meters per second. That's V. Find the frequency of the laser light. So it's asking for frequency, which is F. So since we're trying to get F, we're going to divide V by lambda. So V, as we saw, is 3 times 10 to the 8. Lambda is 633 times 10 to the negative 9. And that gives us 4.74 times 10 to the 14. It's as easy as that. In the quiz that I've set up for my class, I put the last part of it so that you know if you're in the right order or not. So you don't have to put times 10 to the 14 for my answers. You can just put the number 2 decimal places and you're done.